Hey, stats folks! Alright, so hopefully you all did your reading guides, and today we are going to talk about chi-squared tests, or chi-squared tests is how they're actually pronounced, but you'll hear me mispronouncing it probably multiple times throughout this video. So, sorry about that. Okay, so there are some different kinds of chi-squared tests, and today we're going to focus on goodness of fit tests. But first, let's talk about chi-squared tests in general. So, chi-squared tests are used to test accounts of categorical data. Ooh, there we go. Categorical data. So, the three types of chi-squared tests are goodness of fit test, which is used for univariate data, so, one variable. And then you have independence test, which is for bivariate data to see how strongly it's associated. And then you have homogeneity tests, which is for univariate data with two different samples. Okay, so today we are just talking about goodness of fit tests. And by the way, you will often see this written as GOF or GOF tests as well. All right, so once again, goodness of fit tests are used for univariate data, which means we have one variable. And we want to see how well the observed counts fit what we expect the counts to be. So the more the observed counts differ from the expected counts, the more evidence we have against the null hypothesis. Expected spelling. Okay. So, this allows us to determine whether a specified population distribution seems valid. Is what they currently say, what we currently expect, does that seem to be true? So, a chi-squared test. Take a look at this notation right here. This fancy capital X, this is the Greek letter chi. So, we call it a chi-squared test. Now, on the calculator, we're going to use the chi-squared CDF, and so the first thing we would put there is our chi-squared value, and then our upper bound and our lower bound. All right. Okay, so our hypotheses written in words. Okay, we have our null. Oh, yes, it's always important to write these out in words. Don't just half do it and just put like a single word or something. Write it out, express what you're trying to say. So the null hypothesis is the observed counts equal the expected counts. The alternative hypothesis is that the observed counts are not equal to the expected counts. So we're not worrying about so much greater than less than, just simply not equal to, always. Now, always write in context. Like I said, don't be lazy, okay? Write these out in words, in context, and be sure to list the expected counts when you're expressing these. Okay, so an expected count is to find the expected count. What you do is you multiply the proportion of the distribution in each category by the sample size. So it kind of works like population significance tests. So we reject the null hypothesis when chi-squared is too large. If the observed frequencies equal the expected frequencies, then chi-squared will equal 0. Now, let's talk about our assumptions and conditions here. Let me move this up on the screen a bit for y'all. So, first condition, you must have a random sample. It should state somewhere that the sample is random. Okay, you need a large sample size. Okay, all expected counts, keep in mind the expected count, is at least 5. Okay, when we're doing proportion significance tests, our expected counts had to be at least 10. Now, for chi-squared testing, it's at least 5. And then they should be independent. And for independent, as I've been reading through different sources on this, it does seem that the main thing they're interested in here is that 10% of the population rule. So feel free, when you're checking for independence, just to check that the sample size is less than 10% of the population, and you should be good to go. All right, so some properties of our chi-squared distribution. First of all, our degrees of freedom is the number of categories minus 1. So not the sample size minus 1, the number of categories minus 1. All right, now there's little change with an increase in sample size. The number of categories matters far more than the sample size. Now, chi-squared distributions, you can see here, are skewed right. They are not normal, and this is really the first sample distribution that we've looked at that we're not shooting for a normal distribution per se. But that said, as the number of categories increases, increases, the chi-squared curve becomes less and less skewed. You can see here, degrees of freedom 1 is almost an exponential curve, 4, and then 8, and as we do this, it's becoming less and less skewed to the right. All right, now, the mean of this distribution is equal to the degrees of freedom. So mu is equal to the degrees of freedom here. All right, so when we start plugging stuff into the calculator, the first thing we always have to do is find our chi-squared statistic. So chi-squared is equal to the sum of all the observed counts minus the expected counts squared divided by the expected counts. All right, so let's keep this in mind. We're going to be using this. Actually, I'm going to go ahead and stop this video, and we will go ahead and continue on video number 2, and we will go through these examples.